Welcome to For the Love of Physics, and a special welcome today to all the students listening in from Ishik Boys High School.
Yeah, especially Mr. Jager's class.
That's right. We're Mr. Jager's assistants, and we're excited to dive into some physics with you today.
Absolutely. We're going to unpack something you see literally every day. Collisions.
Exactly. Think about kicking a soccer ball, or maybe two cars bumping in a parking lot.
Or even just dropping your phone, though. Let's hope that doesn't happen too often.
Right. These things happen all the time, but how often do you really stop and think about the physics going on behind the scenes?
Probably not that often, but there's some really cool stuff happening.
So that's our mission for this deep dive.
Right.
To unpack the physics of collisions. We're going to look at different types, what happens with momentum and energy, and help you spot these ideas in action.
Sounds good. Let's get into it.
Okay, so collisions. We see them everywhere, like you said. An arrow hitting a target, maybe.
Or a tennis racket hitting a ball. Classic example.
Yeah. And in all these situations, there were two really key ideas we need to keep in mind. Momentum and kinetic energy.
And the first big one, the one rule that applies to every single collision, no exceptions.
What's that?
Total momentum. It's always conserved, always stays the same for the whole system.
Okay, that's a pretty big deal in physics, like a fundamental law.
It absolutely is. Momentum conservation is huge.
But then there's the second concept, kinetic energy, and this is where it gets a bit more nuanced, right?
Exactly. Unlike momentum, the total kinetic energy, it usually changes during a collision. It's not always conserved.
Okay, wait, why? If momentum stays the same, why would kinetic energy change?
Well, it's because that energy of motion, the kinetic energy, it can get transformed into other kinds of energy.
Transformed, like how?
Think about when things collide and, bend or get squished. That takes energy. Some of the kinetic energy turns into what physicists call internal energy.
Internal energy.
Yeah.
Like heat, maybe, or the energy used to actually deform the object.
Precisely. And what about the sound? If you hear a crash, like bang,
Yeah.
that sound is energy. It used to be kinetic energy, but now it's sound energy traveling through the air.
Ah, okay. So kinetic energy isn't lost, it just changes form into heat or deformation or sound.
Exactly. It gets converted. Momentum is about the overall motion of the whole system, which stays constant. Kinetic energy is more about the motion that can be, redistributed into these other forms.
Got it. That makes sense. So our sources mention focusing on two sort of extreme types of collisions to help understand this.
Right. These are like the two ends of the spectrum. We have perfectly inelastic collisions
Okay.
and elastic collisions.
Perfectly inelastic and elastic. Let's tackle perfectly inelastic first. What defines that?
Okay, so a perfectly inelastic collision is when the objects collide and they stick together.
And together.
Yep. They become one combined object after the impact, moving together with the same final velocity.
Oh, okay. Like the example of an arrow hitting a target and sticking right in.
Perfect example. Or think bigger, like a meteorite hitting the Earth and getting buried. It becomes part of the Earth, moving with it. They've stuck together.
So they move as one unit afterwards. How does that affect figuring out the momentum?
It actually makes the momentum part pretty straightforward. You just add up the initial momentum of each object before the collision.
Okay.
And that total momentum equals the momentum of the combined mass moving at its new single velocity after the collision.
So like mass 1 times its initial speed
Right.
plus mass 2 times its initial speed equals a total combined mass times their final speed together.
Conceptually, yes, that's the idea. You just have to be careful about direction.
Ah, right. Direction matters.
Yeah.
So if one car is going right, positive velocity, and hits something going left, negative velocity.
You have to include those positive and negative signs when you add momentum. It's crucial.
Okay. There's a good visual example too, right? Like two cars in a crash.
Yeah, imagine a big fancy sedan stopped at a light and a smaller compact car doesn't stop and hits it from behind. And they get kind of tangled up, maybe the bumpers lock or something, and they move forward together for a bit after the crash.
Right, they're stuck. That's perfectly inelastic.
Exactly.
So in that crash, momentum is conserved for the two-car system. But what about kinetic energy?
Well, in perfectly inelastic collisions, kinetic energy is definitely not conserved. A lot of it gets converted
Converted
into the sound of the crash, for one. And think about the crumpled fenders, the bent metal.
Yeah.
That's the internal energy we talked about. The kinetic energy went into deforming the cars, producing heat in the metal.
So it's inelastic in the physics sense because the objects deform and don't perfectly bounce back. losing kinetic energy in the process. It's different from how we might use elastic day to day, like for a rubber band.
Exactly. Physics inelastic means kinetic energy is converted.
Okay, that makes sense. So that's one extreme,
Mhm.
sticking together, momentum conserved, kinetic energy not. What's the other extreme?
The other end is the elastic collision.
Elastic. So if inelastic means splitting, elastic must mean
Yeah.
bouncing?
Precisely. In an elastic collision, the objects collide and bounce off each other. Ideally, they return to their original shapes, and crucially, the total kinetic energy is conserved, along with the momentum.
Both are conserved. Momentum and kinetic energy.
Yep. In a perfect elastic collision, both stay constant for the system. It's the ideal scenario, really.
Okay, examples. You mentioned kicking a soccer ball earlier. Would that be elastic?
Ideally, yes. The ball flies off, the player's foot recoils slightly, momentum is exchanged, and if it were perfectly elastic, no kinetic energy would be lost.
Or like billiard balls, when they hit each other on a pool table.
Classic example. They click, they bounce off, they go in different directions. That's designed to be very close to an elastic collision. Both momentum and kinetic energy are very nearly conserved.
So hitting a golf ball too. The club hits the ball takes off really fast.
Right. Momentum is transferred from the club to the club slows down, the ball speeds up. And ideally, the kinetic energy of the system just before impact equals the kinetic energy just after.
Or like two soccer balls hitting each other head on.
They just bounce straight back, ideally. A clean exchange, conserving both quantities.
Okay, so we have these two clear categories. Perfectly inelastic, stick together, lose Ke, and elastic, bounce perfectly, keep Ke. But I feel like most things in the real world aren't quite so perfect.
You are absolutely right. Most real-world collisions are actually somewhere in between these two extremes.
In between. How does that work?
Well, think about dropping a basketball. It bounces, right? So it's not perfectly inelastic.
Okay, yeah, it definitely bounces.
But does it bounce back to the exact same height you dropped it from?
No.
Yeah.
Usually a little lower each time.
Exactly. That loss in height means it lost some energy. Some kinetic energy was converted, probably into a little bit of heat in the ball on the floor and the sound of the bounce.
Ah, so it bounced, meaning it wasn't perfectly inelastic, but it lost energy, meaning it wasn't perfectly elastic either.
Precisely. This is what physicists often just call an inelastic collision, without the perfectly. The objects bounce or separate, but some kinetic energy is still converted. Momentum is still conserved, though.
Momentum is always conserved.
Yeah.
Got it. But kinetic energy is lost in these regular inelastic collisions too, just maybe not as much as when they stick together completely.
Right. If you hear a sound during the collision, like the thwack of a tennis ball or even the faint click of billiard balls, technically that's energy leaving the kinetic form. So almost no real-world collision is perfectly elastic.
That's kind of mind-blowing. So perfectly elastic is more of an ideal model.
It is. It's a very useful model, especially in introductory physics. Often if objects bounce off each other in a problem,
Yeah.
for simplicity, we might assume the collision is elastic, even if it isn't perfectly so in reality. This lets us use both momentum conservation and kinetic energy conservation to analyze it, which makes solving things easier.
Ah, okay, so it's a simplification to make the math more manageable when you're learning, unless the problem specifically says energy is lost or they stick together.
Exactly. It's a standard approach to get a good handle on the main principles without getting lost in the weeds of slight energy conversions right away.
That makes a lot of sense. Okay, so let's maybe recap the main ideas we've dived into today.
Sounds good.
We explored collisions. We saw there's a spectrum from perfectly inelastic ones where objects collide and stick together.
Like the arrow and the target or the car crash where they tangle up.
Right. And in those, momentum is conserved, but kinetic energy is definitely not. It gets converted into sound, heat, deformation,
Then there's the other extreme, elastic collisions.
where objects bounce off each other perfectly, ideally, like billiard balls.
And in that ideal case, both momentum and total kinetic energy are conserved.
But we also learned that most real-world collisions are actually somewhere in between. They bounce, but they still lose a bit of kinetic energy.
Still conserving momentum, though. That's the constant.
Always conserved.
Okay.
So, for everyone listening, especially Mr. Jager's students, what are the absolute key takeaways?
I'd say 3 things. 1, total momentum is always conserved in any collision. Period.
Got it. Number 1, momentum always conserved.
2, total kinetic energy is only conserved in perfectly elastic collisions. In all other types, inelastic, perfectly inelastic, some kinetic energy gets converted.
Okay, number 2. Ke conserved only if perfectly elastic.
And 3, perfectly inelastic means the objects stick together after colliding.
Number 3. Perfectly inelastic means they stick. Simple enough.
Those are the core distinctions.
So here's a final thought for you to chew on. Next time you're watching sports, maybe pool, maybe soccer, or maybe you accidentally drop something, try to think about the collision not just as things hitting each other. Think about the flow. Where did the momentum go? Was kinetic energy conserved? Or could you hear or see evidence of it being converted?
Yeah, what kind of collision do you think it was? Elastic, inelastic, perfectly inelastic. It's kind of neat to try and classify them.
Absolutely.
Yeah.
What other collisions can you spot today and see through this physics lens? It adds a whole new layer to just watching the world happen.
Definitely something to think about.
Okay, that wraps up our deep dive for today. We hope this helps clarify collisions for you.
Yeah, keep thinking about these concepts as you see things happen around you.
And remember, stay in contact with your physics teacher. Stay creative.